Yes, so welcome once again to my class. And I don't remember the exact lecture number, but I think this is the fifth class of nuclear and particle physics and lecture number 36 if I am not wrong. Correct me if I am wrong, okay? So, first of all, really very sorry to all of you, okay? Why sorry? Because I can't reply to each and every comment, okay? So there are about I am getting 102 comments. I got yesterday 102 comments, okay? So I am really sorry for that I cannot reply to each and every comment, okay? So just ignore the fact that I am not replying to you, but in case if you have any doubt, okay, if you have any doubt, then you have my number, okay, in case of doubts, okay, in case of doubts, you have my number 724918703, okay. So we were learning about electromagnetic methods. Now let me write something over here that we are studying the methods to determine nuclear size, okay. So electromagnetic methods. So electromagnetic methods, amongst electromagnetic methods we have mesonic X-rays, then we have something called as electron scattering, then we have something called as Coulomb energies of mirror nuclei, Coulomb energies of mirror nuclei, okay. And then we have something called as isotopic shift in line spectra, isotopic shift in line spectra, okay. These are the electromagnetic methods. Then we have nuclear force methods, okay. Nuclear, all these methods are for determining the nuclear size, okay. Nuclear force methods, amongst these we have something called as neutron scattering, then we have something called as alpha scattering, then we have something called as alpha decay, okay. We have something called as alpha decay, and this alpha decay we study in the quantum mechanics, okay. We study this alpha decay in quantum mechanics. So quantum mechanics is yet to be over, quantum mechanics is yet to be over, and whatever the remaining topics are there, okay, whatever you can see on the screen, these two topics from the nuclear force methods, okay, then these four topics from electromagnetic methods, okay, these four topics from electromagnetic methods, nuclear force methods, these two topics are there. So write a note for all these topics, okay, write a note. These topics are to be studied. Super officially as far as UPSC CSE physics optional is concerned. Okay, so these topics in the green box. Okay, neutron scattering, alpha scattering. Okay, then Masonic X-rays, electron scattering. This is already over, by the way. Okay, this is already over. Masonic X-rays is already over in the previous lecture. So these topics: Masonic X-rays, electron scattering, Coulomb energies of mirror nuclei, isotopic shift in line spectra, and these topics are to be studied superficially as far as UPSC CSE physics optional is concerned, because they won't ask they won't ask you the details. Details are required for MSc physics, not UPSC physics optional. So what you need to do, you simply mug up. Okay, so simply mug up this particular part. Okay, simply mug up this particular part. So simply mug up this particular part. The upcoming topics will require deep understanding what this part doesn't. Okay, the upcoming topics will require deep understanding, but this part doesn't. Okay, so that's why whatever I am writing on the screen over here, okay, whatever I am writing on the screen over here, just copy down as it is and mug it up. Okay, just mug it up. Although I will explain you a little bit, but you have to just mug it up. There is no other option. If you want to qualify the exam, you have to mug it up. You don't have to be a intelligent physicist. Okay, you don't have to be that. Okay, so electron scattering. Okay, let me erase this. Electron. So in this method, in this method, elastic scattering of high energy electrons, elastic scattering of high energy electrons is studied. and and from the analysis of scattered electrons are not is computed. So in this particular method, there will be elastic scattering of high energy electrons, means high energy electrons are bombarded, and from the analysis of these scattered electrons, r naught value is calculated. Okay, then the value of r is calculated with the help of the formula. After that, after r naught is computed, after r naught is computed, r is calculated with the help of the formula r equal to r naught a to the power 1 by 3, using that formula. Okay, now why electron is used as a probe? Why electron is used as a probe? So don't be worried. One student had commented that, not commented, he had messaged me on WhatsApp that, sir, the Masonic X-rays which you taught to us in the previous lecture, the Masonic X-rays which you taught to us in the previous lecture, it didn't satisfy my heart. Okay, while studying, it didn't satisfy my heart. So keep this thing in mind that you have to qualify the exam. You don't need to be an expert of physics. So if you want to teach in the future, then you can study obviously. But the thing is that, if you want to be an IAS officer, you must focus on the exam. Okay, instead of learning. So the focus must be much of the exam oriented pattern. Okay, so so whatever superficially I taught you in the Masonic X-rays experiment, those things you have to mug up superficially. Okay, so this particular part is superficial. I don't say that the entire syllabus of physics optional is superficial. No, only this particular part, that is the methods to determine the nuclear size. Okay, the methods to determine the nuclear size, this part is superficial as far as exam is concerned. Okay, but if someone is doing MSc in physics, then he or she must study that in detail. No doubt about it. But as far as UPSC physics optional is concerned, these topics are not to be studied in depth. Okay. Now, why is electron used as a probe? Now we will calculate the de Broglie wavelength of electron. If it comes out to be in the range of nucleus, okay, you know this very well, that in order to get scattering results, okay, in order to get good scattering results, in order to get good scattering results, we need the de Broglie wavelength of the projectile to be near about the same as nuclear size. So to get good scattering results, okay. So in order to get good scattering results, we need the de Broglie wavelength of the projectile to be nearby, okay. Nearby the same as nuclear size, okay. Near about same. Let me tell you one thing, okay. So reduced de Broglie wavelength reduced de Broglie wavelength of electron, what is it equal to? It is equal to your lambda cut equal to lambda divided by 2 pi, which is equal to your h by 2 pi square root of 2me, okay, and which is equal to your h cut divided by square root of 2me. Okay, so this is the reduced de Broglie wavelength of an electron. Okay, now E is equal to, we take in the experiment E to be equal to 200 mega electron volt. So 200 mega electron volt, when we put the value of E to be equal to 200 mega electron volt over here in this particular equation, when we put the value of E to be equal to 200 mega electron volt, so we get lambda cut value to be equal to 10 to the power minus 15 meter. Okay, so it interacts, so that's why what happens is that it interacts strongly with the nuclear charge. Okay, so it interacts strongly with the nuclear charge and is a fit candidate for probe. Okay, so electron, when it collides with the nucleus X, okay, it yields you nothing but the same thing. Okay, only the energy difference is there. Okay, energy is redistributed. Okay, what does this equation imply? Nothing changes, only the energy is redistributed. Now we will learn about the Hofstadter. Okay, Hofstadter experimental arrangement. So Hof Hofstadter experimental arrangement. So how to pronounce this? It is like this: Ho Hofs. Okay, Hofstadter. Okay, Hofstadter. Hofstadter. It's like this. Pronunciation is like this. Okay. So your the experimental arrangement, just you have to mug it up. It looks something like this. Okay, this incident beam will come over here. Okay, then this is incident beam of high energy electrons. Okay, incident beam. Okay, this is your beam, incident beam of high energy electrons. So there is a very thin target over here. Okay, over here some foil kind of thing will be there, thin target. This is your beam collector. Then your beam will go like this. Okay, it will be deflected at an angle of theta, right? So this is your basically detector. Okay, this is your what? Detector. This is your detector. So this is the Hofstadter experimental arrangement of this electron scattering. If you want to have more clarity on this topic, then you can surely have a look at the books, okay, but no need to do that, because in the examination this particular part is asked very superficially. So plus Ze, so this is basically nucleus, your nucleus, okay, plus Ze, and this is the deflection of your electron. This is negatively charged electron, it is getting deflected by an angle theta, okay. In the electron nuclear collision, then write over here, in the electron nucleus collision, in the electron nucleus collision, the electron loses kinetic energy and the nucleus recoils. So in electron nucleus collision, the collision of this kind, like the one I showed over here, okay, like the one I showed over here, the electron nucleus collision is there. This is your nucleus, right? This is your nucleus. Let me show you the nucleus. This is your nucleus and this is your electron. So collision is taking place. Electron will lose some of its kinetic energy, and nucleus, as it is heavy than the electron, as the nucleus is heavy as compared to the electron, so obviously the nucleus will recoil, because heavy objects recoil, okay, light objects get bombarded and heavy objects recoil, okay, so the nucleus recoils. This scattering is just identical. Now this scattering is just identical. This is just identical to Compton scattering. What happens in Compton scattering? Do you know? In Compton scattering, you know this very well, that there is a metal and electrons are bombarded on it. Okay. So basically, that is photoelectric effect. Electrons are bombarded on the metal. That is photoelectric effect. But Compton effect is also similar to that only. Okay. No, in Compton effect, electrons are bombarded. In photoelectric effect, photons are bombarded. Okay, so that's the difference between the two. In Compton scattering, electron is bombarded, and the nucleus recoils. And in case of your photoelectric effect, photons are bombarded and electron recoils. In case of photoelectric effect, so the theory of quantum scattering, it is a complete theory, and we need not go into the theory. So let E is equal to energy of the incident electron, energy of the incident electron, En is equal to energy of recoil nucleus. Okay, m is equal to mass of the nucleus. Theta is equal to your scattering angle. So from the theory of quantum scattering, now don't go into the proof of this equation which I am going to write over here, okay, because it is not required for you. So just mug up, okay, this particular part from the theory of Compton scattering. En is equal to E square over mc square 1 minus cos theta divided by 1 plus E by mc square 1 minus cos theta. Okay, let this be your equation number 1. So this is from the theory of quantum scattering. Energy of the scattered electron is energy of the scattered electron is energy of the scattered electron is like this, E minus En. Let this be your equation number 2. Okay, now why this is the energy of the scattered electron? You know this very well that when electron will approach the nucleus, when electron will approach the nucleus, initially it will have some energy. Let's suppose that energy is E. Okay, now after it gets scattered, after the electron is scattered, the energy will be, suppose its energy is E dash. Okay, and suppose the energy imparted, to this nucleus is En. So what will happen? E dash will be, your E will be equal to, basically your initial total energy will be equal to this is scattered energy, so E dash plus your En, that is means nucleus, the recoil energy of the nucleus. Okay, so En. So what will happen when we write E dash? E dash will be E minus En. E dash will be your E minus En. Okay, so this is your equation number 2. The adjacent figure, so this figure, okay, the Hofstadter experimental arrangement figure. Okay, let me see over here. Yes, so just a second. Okay, yes, so your probability of scattering is something of this kind. Okay, you will have to draw these things in your notebook. This is your y-axis, this is your x-axis. So probability of scattering, it will be over here. Okay, and it will be something of this kind. Then we have something of this kind. Okay, then just let me erase this x-axis from here. Okay, and let me redraw it somewhere else. Okay, let us draw it over here. Then what will happen? So it is like this. Okay, this is for indium and this is for your calcium. So this is for calcium 40, this is for indium 115, this is for gold 197. So this is your probability of scattering on the y-axis, and your angle of scattering is on angle of scattering theta is on x-axis. Okay, then we have one more graph over here, which is rho r. Okay, and I will explain this graph to you. Okay. Now actual charge distribution is like this. Okay. Okay. This dotted shows your actual charge distribution. Actual charge distribution. And this is step function. This is basically your step function, right? So what does this mean? This actual charge distribution, the dotted line which actual charge distribution it is showing, it basically shows your quantum behavior. Okay, quantum behavior. That means that when we start moving away from the nucleus, this is suppose the center of the nucleus. Okay, suppose I draw the nucleus like this. Okay, suppose the nucleus is like this, and suppose this is the center of the nucleus. Then what should happen? Ideally, ideally what should happen is that as we move away from the nucleus, and as soon as we reach the edge of the nucleus, the graph should fall abruptly like this. Means the probability of finding the nucleon, means proton or neutron, the probability of finding the proton or neutron in this particular region. Okay, probability of finding the proton or neutron in this particular region, it should abruptly fall to zero after a certain radius. After a certain radius, after a certain radius, it should abruptly fall to zero in case of classical mechanics, because in classical mechanics there are sharp boundaries. But the actual charge distribution looks something like this. Okay, the actual charge distribution looks something like this. Means there is not abrupt fall in the probability of finding. It means the probability of finding the proton or neutron, means nucleon, it does not abruptly fall to zero. It will it will it will reduce and reduce and reduce, and then it will be little bit constant, and then it will reduce to zero eventually, slowly. Okay, so this is the meaning of this. And what is the meaning of this? These are the probability of scattering, and theta for various elements. This is for gold, this is for indium. The graphs are like that. Calcium is over here. The graphs look something like this. Okay, so let me write over here. Let this be figure number 1. This is what your figure number 1, and let this be your figure number 2. Okay, so what happens is that the figures 1 and 2, the figure 1, the figure, you have to draw this in exam, and you have to write just like this. Okay, don't go into the details. The figure 1 shows the angular distribution of elastically scattered 200 mega electron volt electrons from nuclei assumed to have spherical. Now this is the idealistic graph. Ideally the graph, this is what is your ideal graph. Ideal graph. The ideal graph should look like this, but in reality for various elements the graph shows deviation. Okay, in reality the graph shows deviation. So figure 1 shows angular distribution of elastically scattered 200 mega electron volts electron from nuclei assumed to have spherical uniform charge distribution. The actual nuclear charge distribution, the actual nuclear charge distribution is not exactly given by a step function, but is shown by dotted line in figure 2. Okay, so I am drawing the figure 2. Let me draw the figure 2. So let me once again draw the figure 2 because it was not systematic. Okay, so now it will look something systematic. Okay, so this is what is this? This is your rho r. Okay, this is your r. So what is your actual charge distribution? It goes something like this. Okay, it goes something like this. So this is what is your actual charge distribution. Okay, actual charge distribution. Okay, so what is the function associated with this curve? Okay, the function associated with this curve is like that. I am showing in the next page. Hofstadter assumed that the nuclear charge density has the form like this. This is the form E r minus r divided by b. This is your equation number 3, and this from this function, you know this very well, you must have learnt in maths in lower classes that to every function there is an graph associated. To every function there is a graph associated. So this is a function of r, so there will be a graph associated with it. So the graph has been drawn over here. The graph is this dotted one. Okay, so graph is this dotted one. So see here rho naught is the density at the nuclear center. At the nuclear center, r is the radius at which rho falls to rho naught by 2, means the probability of finding the nucleon. R is the radius of nucleus. The nucleus radius is defined as the distance at which the probability of finding the nucleon falls to half. Okay, and B measures how rapidly rho falls to 0 at the nuclear surface. At the nuclear surface. Okay, probability of scattering is equal to your intensity. Probability of scattering and intensity. Probability of scattering is also called as intensity of scattering. Okay, intensity of scattering. So over here in the figure, which figure? This probability of scattering. It can also be written like this, intensity. Over here in this figure. Okay, intensity can also be written in that place. So this analysis determines a nuclear radius R. This analysis determines a nuclear radius R that grows with mass number A according to the formula. R equal to R naught a to the power 1 by 3. Now the various values which are found are like this, with R naught equal to 1.32 femtometer for a smaller than 50. Okay, and R naught is equal to 1.23 plus minus 0.01 femtometer for a greater than 50. So let's understand this. Probability of scattering is also called, this I told you, this analysis determines a nuclear radius R that grows with mass number A according to the formula. This is self-explanatory. With R naught equal to this for A smaller than 50, R naught equal to this for A greater than 50. Now the Coulomb energies of mirror nuclei we will do in the next class. Okay, Coulomb energies of mirror nuclei we will do in the next class. So thank you very much. If you haven't subscribed to our channel, then please do subscribe to it, and if you like the video, then please do like it. Okay.